Hello everyone, I'm Yiwei Bai. I'm going to present our paper, CLR-DRNets, Curriculum Learning with Restarts to Solve Visual Combinatorial Games. This paper is a joint work with Chen and Carla Gomes. Deep learning has surpassed human-level performance on many perception tasks, leveraging a huge number of data ranging from object recognition to language translation. However, humans can tackle these problems, combining their perception and reasoning abilities, using only a few data. We consider unsupervised or weakly supervised visual combinatorial games. They capture various real-world applications, particularly scientific data interpretation tasks, which in general have few data but for which rich prior knowledge is often available. We focus on sudoku-based visual combinatorial games. Sudoku is a classical number placement puzzle where you want to fill in digits into these cells, and one digit can only appear in each row, each column, each 3x3 blocks once. We consider two games. The first is the visual sudoku, where we replace the digit with its corresponding image, and 0 means empty cell. The other game is the visual mixed sudoku, where we mix two visual sudoku into one visual mixed sudoku. The goal is to demix them and fill in all the missing digits. CLR-DRNets borrowed the general idea from DRNets, deep reasoning nets. So we here do a brief intro to DRNets. DRNets is designed to solve unsupervised pattern demixing, leveraging the prior knowledge. Prior knowledge often involve combinatorial constraints with discrete variables, which are hard to be optimized using deep learning. DRNets propose an entropy-based continuous relaxation scheme to encode general discrete constraints, such as sparsity, cardinality, and all different constraints. DRNets formulate the problem as an unconstrained optimization problem. We propose CLR-DRNets based on the general DRNet framework to learn to solve visual combinatorial games, only supervised by the game rules and image prototype through combining perception and reasoning seamlessly. So here, image prototype will tell the model what digit 1 image look like, what digit 2 image look like. We boost DRNets through an enhanced reasoning module to generalize to the unseen data. A curriculum with restarts learning framework is proposed to tackle the difficulties in the learning and testing process. CLR-DRNets consists of three parts: perception module, decoder, and reasoning module. Formally, CLR-DRNets learn to solve visual combinatorial games through optimizing the loss function below. F theta p means the perception module, and psi p are the constraints applied on the output of the perception module, which we refer to it as the initial estimation. F theta r is the reasoning module, and the psi r are the constraints applied to the output of the reasoning module, and we refer to it as the reasoning output. L is any reconstruction metric like the L1 loss and L2 loss. CGAN means the conditional generative adversarial network, which is used to reconstruct the input based on the output of the perception module and the reasoning module. Lambdas are the weight scalars. Here is the overview of CLR-DRNets for visual sudoku. We use 4x4 sudokus here for easier illustration, but for all of our experiments, we use 9x9 sudoku. The blue part is the perception module, which consists of two ResNets. And the orange part is the enhanced reasoning module that consists of one modified lstm. The red part is the decoder that consists of one conditional generative adversarial network that is pre-trained on the prototype of images. The input is a visual sudoku, and the input format is a batch of images of all the cells. The visual sudoku is fed into the perception module. The top ResNet will compute the shape embeddings of all the possible digits per cell, which means that for each cell, it will generate 5 shape embeddings that correspond to digits 0 to 4. You can regard shape embedding as a sort of latent space that can describe what the digits look like. The lower ResNet will compute the initial estimation of the visual sudoku. You can understand it as it is trying to understand or translate the visual sudoku into a probabilistic standard sudoku. Then this probabilistic standard sudoku will be fed into the modified lstm to compute the reasoning output. If we take the argmax of the reasoning output per cell, it is supposed to get a valid sudoku. Then, based on this reasoning output and the sudoku rules, following DRNets continuous relaxation scheme, we can derive the reasoning loss. For the SIGAN, it will take the shape embeddings as input, and for each cell, it will generate 5 images, which correspond to digits 0 to 4. Then we can weighted sum these 5 images based on the reasoning output. Then for each cell, we can get a reconstructed image. Now we can compute the reconstruction loss based on the reconstructed one and the input one. Here is the overview of CLR-DRNets for visual mixed sudoku. The idea is quite similar with the visual sudoku. For the perception part, two resonate both into two branches, one branch for the digits, another for the letters. For the decoder, we also need two conditional gains, one to generate the image of digits, another to generate the image of letters. For the enhanced reasoning part, the modified lstm is not changed, but we need to pass it twice. Now we are going to introduce the modified lstm, long short-term memory. Before introducing the actual architecture, I would like to introduce two terms. The first term is the constraint graph. Constraint graph is a square metric where each entry represents the constraints between these two elements. For example, consider a 4x4 sudoku. Its constraint graph will be a 16x16 metric. Each row represents one cell of the original sudoku, and each column also represents one cell. The entry is said to be 1 if two cells correspond to the entry, belong to the same row or same column or same 2x2 block, otherwise 0. The sudoku embedding is to replace the digit with a vector, since vector is easier to be understood by a deep neural network. Now let's look like this modified lstm architecture. The black rectangle means sudoku embedding, the gray square means constraint graph, the black dot means metric multiplication. This means the concatenation. This H means the hidden state, and this means the lstm unit. This is the input. So the input of the first unit is special, which is the concatenation of sudoku embedding and sudoku embedding multiplied by the constraint graph. The input for the other unit is the concatenation of sudoku embedding and the last unit's hidden state multiplied by the constraint graph. And the final hidden state will be connected with the fully connected layer to compute the final output. Now we introduce the training strategy of CLR-DRNets, the curriculum learning. Perception task is generally easier than the reasoning task in the visual combinatorial games. For example, you can easily train a model that can perfectly classify the digits 0 to 9. You can achieve like 99.9 accuracy on the test set. But it's really hard to train a model to solve the sudoku, though I give you the clear sudoku input and the sudoku label. So we need to carefully select the sequence of training examples to address the difficulty imbalance issue, or the model may only focus on the easy part and stuck in the local minimum. Formally, we identify a set of constraints that are hard to optimize. Then we set an initial difficulty level and increase it when our model does well on the current level. Then we can stop this process when our model does well on the difficulty level that we want. Now we are going to talk about the training mode of the CLR-DRNets. We propose two training modes that can cover different scenarios. The first one is the joint training, where we learn the parameters of the perception module and the reasoning module jointly. This can handle noisy input training examples. Here, noisy means the input is something like an image, not the clear digit. So you need a method to identify the input. However, you cannot find a perfect method to identify the input. So this may introduce noisy for your reasoning step. The separate training is the second mode, where we separately train the perception module and the reasoning module. This requires clean input training examples, but still no label required. Here, clean is compared with the noisy, which means that the input is clear digit, so no noisy for the reasoning module. Joint training requires less supervision but cannot do as well as the separate training, where the separate training can achieve a higher accuracy. Now we are going to talk about the testing strategy, restarts. We have observed that the validation accuracy is increasing smoothly during the training time, but the instance the model can solve varies significantly. So we can select several models based on the validation performance from the same training trajectory and apply them to each test instance one by one. Note here, from the same training trajectory can ensure that we do not incur too much overhead for the training time. Also, we do not need to apply all the models to one instance at the test time. If the instance is solved, then we do not need to apply the rest models. Also note that our loss function is derived without label, so we can still optimize the model a few steps for a specific instance in the test phase, which only takes few time. For instance, in our Visual Studio examples, we will train the model for 20 more steps in the test phase. This only requires less than 1 second, so it's pretty fast. We are going to talk about the experimental results on Visual Sudoku. We consider two types of Visual Sudoku, the digit Visual Sudoku and the letter Visual Sudoku. In digit Visual Sudoku, we replace the digit 1 to 9 with the image 1 to 9, and we use 0 to represent empty cell. In letter Visual Sudoku, we replace the digit 1 to 9 with the letter A to J, and we use O to represent the empty cell. The top table shows the digit Visual Studio test accuracy. We compare CLR-DRNets with DRNets, SetNet, CFN, HOCOP, HOCOPC. Here C means the model calibration is done using validation set. Finally, it's the ResNet plus set solver. For the average 36 hints dataset, we can find CLR-DRNets outperform all the other baselines using less supervision. DRNets cannot really learn, it can only solve, and which requires a lot of time, while SetNet and CFN requires label. HOCOP and ResNet plus set requires a set solver. For the 17 hints dataset, note that 17 is the smallest number that the Sudoku can have unique solution, so it's really hard. We can find that DRNet and SetNet cannot solve anything, but CLR-DRNet can still get a very high accuracy, and it's only slightly worse than the ResNet plus set. The reason that ResNet plus set can achieve very good accuracy on 17 hints, since there are a lot of zeros, which means empty cell, in the 17 hints dataset. So ResNet can achieve almost 100 accuracy on identifying zero, so its performance is improved a lot compared with the average 36 hints dataset. The bottom figure shows the number of hints versus the letter Visual Studio test accuracy. We compare CLR-DRNets with DRNets and ResNet plus set. We can find that CLR-DRNets consistently and largely outperform the other two methods. Here, the ResNet cannot have as high accuracy as it has for the digit, so its performance is really bad here. Now we are going to talk about the experimental results on visual mixed Sudoku. To form a visual mixed Sudoku, we need to mix one letter visual Sudoku and one digit visual Sudoku using the max operator. This figure shows the number of hints versus visual mixed Sudoku test accuracy. We compare CLR-DRNets with DRNets and ResNet plus set. We can find in all the number of hints cases, CLR-DRNets largely and consistently outperform DRNets and ResNet plus set. And for most number of hints cases, CLR-DRNets has a very high accuracy, while the other two methods cannot solve anything. Now we are going to talk about the evaluation study. We conduct the evaluation study to show the contribution of curriculum learning and restarts. This table shows the performance of different tasks, and we report the performance in proportion to CLR-DRNets results. This means the CLR-DRNets without curriculum learning. This means without restart. This means CLR-DRNets without restarts plus curriculum learning. So we can find that for Visual Studio 17 hints and Visual Mixed Sudoku 20 hints. Both curriculum learning and restart contribute largely to the performance. but for visual mixed sudoku 25 hints. Restarts didn't contribute too much to the performance. We postulate that the visual mixed sudoku 25 hints is not that difficult, so only one model can learn the problem structure very well, so we do not necessarily require restarts to get a very good accuracy. And this application study may also explain why the restarts work well in the practical time. Since the problem is really difficult, so one model is really hard to capture the entire problem structure. But we surprisingly found that during the same training trajectory, different models learn very different parts of the problem structure. So a set of models can capture the problem structure much better than a single model. Then if we imply a set of models in the test phase, the performance can be improved a lot. Here we summarize our contributions. We propose CLR-DRNets, curriculum learning with restarts to weekly supervise learn-to-solve visual combinatorial games through combining perception and reasoning abilities. CLR-DRNets outperforms the state-of-the-art methods for solving visual combinatorial problems using less supervision. Thanks for watching. Here is the QA session. Thank you.